All right, welcome. All right, a reminder that there is an assignment due tonight, the discussion. The course orientation quiz, if you haven't taken that yet, you need to make sure you take the course orientation quiz. There's also your background information, so that's also one that's due tonight. Some of you had asked about that last time. It had a due date of Tuesday, so now it was moved till Thursday, and so please submit that one also. So 3 assignments are due by tonight, and then your quiz will be available starting at midnight tonight and go for all day on tomorrow. Any questions about that?
It says it's due today, but there's no quiz to click on. I think I already did it. Yeah, I saw it. Oh, I did it backwards.
So some of you said you have submitted it.
I think so.
It didn't have.
But we did it like last week. Yeah. If you did it early last week, I think you were fine.
Okay.
The incoming knowledge.
Okay, I will check this because it's taken forever for this to load. I'll check this as we do our first activity. All right, any other questions, comments, concerns about anything? Okay, so I'll get back to you about the learning knowledge quiz. Otherwise, make sure you submit the homework by tonight and the course orientation quiz. Any question about previous material? So last time we went through the voltage dividers, current dividers, and then we talked about the potentiometers and some of the sensors. Any questions about any of that material? You guys ready to move on? Okay, so a very common circuit that you're going to see is called this Wheatstone bridge. And there is this Robo-B. It's a really cool little tiny. Oh, I thought I had the video of this. Okay, so we're going to skip over to the video. You find the video. Okay, here's this.
This is a Robo-Bee. These miniature robots are inspired by the biology of bees and hive behavior. New materials, compact high-energy power sources, and new control systems, and a new method of self-assembly and pop-up manufacturing. I'm Elizabeth Farrell, a PhD student at ECE. I am energized by the potential of an autonomous device that thinks on its own. It could impact everything from crop pollination to search and rescue. And that's science, not fiction.
Okay, so there are these little tiny robots. They're really cool. So on this, OBS go. On these little tiny Robo-Bees is they have this ocelli that you can see there, that little pyramid. And what is on there is this kind of these sensors. And so they're using these sensors to detect how the wing needs to be moved. And so it can fly in different directions, avoid hitting things. And so a lot of this data becomes a challenge of how do they actually use this. So this took the idea of bees that use their antenna to actually determine wind speed. So as it's blowing by them, they're able to detect using the sensors that are in their antenna. And so how could you actually detect the presence of wind on something like this? Any thoughts? Okay, so pressure would be one. Yeah?
I would just say just nerve endings, kind of.
Okay, so like on the antenna, it's going to be the little fibers are detecting the move, like they're actually moved by pressure or wind itself, and so that gives them a different sensation. So we can't interpret sensation. So as you know, if we were going to do this, a change in pressure could be something, or as I went through last time with the different sensors, there needs to be a change of something. And so this gets us to a different type of sensor called a strain gauge, where a strain gauge has resistances that are measured between them. So as you deform something, it actually will detect the difference and give you a resistance value difference between those two. And so you could use actually a strain gauge and be able to understand like, oh, the wind is blowing it down more, so that resistance means that this is in this actual degree change, or it's changing it up, and so that resistance value means that it's changed it up. And use those differences in resistance to then build smart circuitry to say, well, that change means like I need to actually intelligently do this to the wing instead to make it fly. So a strain gauge on a bee of an antenna has actually been done, which is kind of cool. So small little strain gauge on a antenna, bee antenna. So as the wind came down, it created the strain gauge change, and that changed the resistance. So looking at this, like we want to know, well, like how do we actually measure this now in a circuit? So this would be kind of the beginning thought of, well, why don't we have the one that changes, this resistance that changes it, compare it to another resistor that's going to be a fixed value that we already measure and know what it is, put a voltage on it, and then that can maybe tell us some differences. So let's look at this. If we were to try to compute this V out, again, I'm going to put a reference point in here of 0 volts. If I was to write the equation, what do I notice where V out is being measured? It's being measured either in the pathway between here and here, or it can measure the pathway from there to there. Either one would be correct, right? If I find it from the pink pathway, I need to know the voltage of Vx, and I would need to know the voltage across R1. So if I took that pathway, oh, I forgot. This is a new concept. So having a wire just in a circuit anywhere, this wire just means that I am, have you guys used the multimeter yet? You haven't yet. Oh, yeah. Okay. So on the multimeter, if you take the red probe and actually stick it in the circuit somewhere, that's acting like that wire there. So that red probe is where that wire is gone. Then I'm going to place the black probe on the 0 volts, and that's going to give me the measurement. Hopefully you can see here, though, that the pathway that it measures is either across the strain gauge or either across the pink one, and they're in parallel to each other. So this would be my red probe of multimeter. So I would label that as a plus, and then it is comparing it through the multimeter. So there's going to be, your multimeter here. And it's going to put your black probe and so you're not going to see this multimeter being drawn in the circuits. And what you're going to need to know is anywhere I see a dot with a label, that means that I have put that red probe on there and I'm measuring it in comparison to ground. So physically that's what's happening. And then to get the actual equation of what is happening, we have to look at the circuit itself. So it can be either a pathway, I can take a pathway from the left to the right, or I can take it from the right up. I'm going to start here and go in this direction. As I do that, change colors. I'm going to do it in blue. So if I go in this direction and around this way, it's going to be a plus Vx minus VR1, and then it would be across the V out would be a minus. So my loop would be plus Vx minus VR1 minus V out equals 0. So in this case, V out, I would need to know Vx and VR1. Another pathway would be going through here through V out, and that is going to be the voltage across this R strain. So V out is going to equal, well, let me go backwards. Okay, so a plus and then a minus. So plus VR strain is equal to V out. Sorry, minus V out equals 0. And then you can say that VR strain is equal to V out. Do you recognize what this circuit is? I heard somebody say it.
Voltage divider.
Correct. It is a voltage divider. So we can find VR strain right away. If I don't identify it as a voltage divider, I notice it only has one loop, so therefore I can find the current and then take the current times the resistance to give me the voltage across those elements that I need to find. Noting that it is a voltage divider, and if I find just this one voltage, then that would be easiest. So the voltage across R strain, I know, is going to be Vx times R strain over R1 plus R strain. How do I know that it's positive? How do I know this is positive and not negative? Any thoughts? So whatever orientation the battery is, so in this case, if it's plus to minus, if my current is going in this direction, it would be plus to minus. So if they are matching this, this will be a positive. If instead I have a voltage and I'm trying to actually find it here to here, minus to plus, and my current is going to still go this way because of the set direction of the battery, which is a plus to minus, then this would be a negative. So these are opposite. Does that make sense? Yes. Okay. So what about, okay, top one here. Is that going to be a negative or is that going to be positive? Correct, it will be negative because the current is going to go in this direction, which is opposite. Okay, what about the bottom one? Correct, somebody said it, positive. Yes?
So I'm a little confused on
how we were able to determine the ER strain minus the V out is equal to 0?
This one up here?
Yes.
Okay. So even though the multimeter is not connected, you're going to have a physical connection there with the wire probes. That creates a closed loop to be able to do a circuit or a voltage pathway. So you can go from ground back to ground as long as you know a voltage difference, even if it's not connected. So your pathway here from ground is through our strain and then back down through the multimeter to ground. And that gives you the pathway from ground back to ground. Is that more clear then? Okay, so that's the same on the top pathway. You're using that as a pathway to get from ground back to ground. So going forward, you won't see the multimeter there. You'll see a plus to a minus, and that would be a pathway still that you can take for the voltage loops. Will current flow through this? Right here. Is there current here? I heard somebody say it. Is there current here? It's a floating wire, so there's not going to be any current there. So there's only one branch, so one current, and the same current is going to flow through here and here. Yes?
It's like a floating wire, then the wires like aren't connected inside the multimeter.
So there's a huge resistor in there that's preventing any current from going there. And it's huge. So yes, there will be a little bit of current that trickles in there, but it's like picofarad, femtofarad, or femtoamps.
Gotcha.
So we basically ignore it. So we assume that it's acting like an open and therefore no current flow. But even though there's no current flow, you can still have voltage. So you can have a voltage just like a battery is sitting there. And it has, you kind of look at it as it's being open. So you're just measuring like across a battery without a connection fully to everything else. Does that make sense? Okay. Any other questions? Okay. All right, so now let's look at two dividers. So on this, I'm going to call this one VA and this one VB. And so go ahead and write the equations for, well, we already really pretty much wrote the one for VA. So write the one for VB. So I'm just going to rewrite this again. So go ahead and write the equation for VB.
That's a reference point. I'm forgetting the reference point. Okay, so now I get it. Now yeah, so like if the curve is in the top left, then it'd be then to ground.
Okay, so it looked like there was a good consensus. So people did find that the voltage was across R3. So R3 times Vx over R2 plus R3. All right, questions about that? Yes.
Can you just walk through that little slowly?
Okay, so this came out with another student. You got to remember where your reference point is. So that 0 volt reference point is where you're comparing to. So if you have VB and you're referring it, like you're trying to figure out between that point and ground, that's going to be the voltage across R3 that you're trying to find. Do you see that part?
Yeah.
Okay. So knowing that the division of this, the current is going to go around in this way. It goes out of the plus of the source around back to ground. So that's going to be a plus minus here and a plus minus here. So they're the same polarities. So you're going to get a plus polarity here. And then from the voltage divider, remember that you're taking the resistance you're trying to find it across, so R3 in this case, times Vx, and then it's R3 over the total in the whole branch, so that's R2 plus R3. If you don't see that, you could say that, okay, let me label this I, and then I can take a loop and go through these. If I go through in this direction, it would be a plus, plus, minus. And so this would be plus, and then as I go across that voltage, it's going to be I times R3 plus I times R2 minus Vx equals 0. And then solving for I here is Vx over R2 plus R3. And then VB would be I times R3. And that gives me the same equation. So if I don't see that it's a voltage divider, I can still do my voltage loop around, solve for the unknown there, which would be I, and do it that way. Did that answer your?
Yes.
Okay. Any other questions? Yes.
Why is it R3 instead of R2?
So R2 is only going to be the voltage between here and here. So if I just wrote, this would be Vx R2 over R2 plus R3. And if that's the voltage there, it's only across R2. So in order to find VB, it would be Vx minus that to get VB. So you could say it's this minus Vx R2 over R2 plus 3, R3. But you can't just say it's just the resistor, the voltage across R2. And that's because of where the ground is located. Does that make more sense? Okay. Other questions? Yes.
So it's only through R three, the presence is
It's only R3 what?
it's only through R three because of B, or VB, because of the wire.
It's where the 0 volts is. So because you're comparing it to where that 0 volts is, where VB is, correct, yes. So if VB was at the top, then it would just be Vx. If you had VB, like if you were measuring here, that would be just Vx. Okay, other questions? Is there another hand? Yes.
So is the general rule that, if you're using that equation, R3 would be on top because it's the last resistor of the volts? Is that?
It's because it's connecting it between here and ground. So you gotta look at where is your ground. And so from ground to that point, there's only the resistance R3. So that's the only branch that you're going through. And so you're using R3 because that's the voltage you need to find. Let me do one more. Okay. Okay, thinking of these as like elements. And each one is kind of going to ground. Let me do 3. 1, 2, 3. Okay, so say I have these different branches. With it drawn this way, hopefully these are easy to see that these are in parallel to each other. In each of these, if I am trying to find the voltage here, it can be either the sum of the voltages in this branch, or the sum of the voltages in that branch, or the sum of the voltages in this branch. Because all of this ends up being, this is all the same node up here. Sorry, let me draw these a little bit better. Okay, I'm gonna stop at the, okay, so this is all the same node. And then the branches are actually at the end of the elements. So. Does that, I don't know if that helps clarify. So if that voltage, if that node is, if you're trying to find that node voltage, then you could do any of these and they're all gonna equal the same. So if I hook this up to a battery here, say I go and connect this to a 3-volt battery. Now I know what this node value is. It's 3 volts. So the voltage across this element is 3 volts. The voltage across both these elements is 3 volts. And the voltage across all 3 of those elements is 3 volts. Then each of their currents is going to be different because these elements are different. So this will be one current going through all 3 elements. This will be, well, that didn't contrast very well. And then this will be a separate current, I2, that's different than I1. And then this one will be another current, and all, because it's in one branch, it will be all the same. Does this make sense?
Like for all 3 of these branches, would they be like -3 volts to get back down to 0 at the grounds, or would it be positive?
So each one of these is, so right across this is going to have plus to minus to be 3 volts. So across that element, it has to be 3 volts. the combination of two elements has to equal, because it could be 1.5 volt plus 1.5 volt, or it could be 1 volt and 2 volts. It just has to add up to 3 volts across both of them. And across 3, it would be then a division of the 3 volts. If those 3 are resistors, across each one, you're going to have, so say these are 3 resistors in there. Across each one, you're going to have a division based on their value over the ratio of all 3. So it gives you that percentage of how much is over each one. Does that make sense? Okay. So I wanted to kind of make sure you guys get this concept because you need that to keep going forward. So very important concept that you see that this is the same. So in this diagram, the branches are curved, and I could do the same thing down here. I could redraw this. And instead of having nice straight branches here, I could actually say, well, I want to draw this one a little bit weird. So I'm going to make this branch a little different. And I'm going to go up first and put an element there, and then I'm going to go down, put an element there. I'm going to go sideways, put an element there. I'm going to go back around and curve it around and go here. And I'm going to make a branch that looks like that. It's the same thing though. It's still one branch. Even though it curves and it turns and it goes all over the place, it's still the same branch. So once I've hit that element, I know like, okay, now this is a new branch. So I'm going to follow that branch until it hits an extraordinary node. And in this case, it doesn't, but I could have a case where it also came and then here it split again. And say it had something that looked like this with 3 elements in there. So this would continue and hit those and then go into 2 parallel branches that once joined is the same branch as the yellow. But I wanted to demonstrate this because this concept, these 2 are in parallel. And can be rejoined as one. So I could make an equivalent circuit here and connect that in here instead. And then that would be a continuation back to yellow through to ground.
And then would you make another equivalent, like between all the other resistors and then find voltage across like the total?
Correct. So if they were all resistors, I could just join those, like the 3 on the left would become 1 as in series. That would be in parallel with the second branch. And then this third branch would be those 3 in series at the top, 2 in parallel for 1, and then add them all together once you formed them into parallel. And then that could be all one resistance, and you can find the current that way to all of them from that 3 volt source. And that would help you to be able to get this current here, I. And then it could divide them out, and you could do a current division if you wanted. Does that help? Did you have a question? Okay. So these are all the same. Even though you have curved wires here, they are the same as far as they're same as a branch. So up here is the same. We have that VX, and here we only have 1 branch, but the concept of them is the same as far as if you're trying to find, once you put VB in there, you've created an extraordinary node because you've added in, well, no, take that back, don't think of it that way. You're just probing it to find the voltage. So you're not changing the circuit, you're just changing the pathway. So you have a pathway through the pink and you have a pathway through the yellow. And either one of those is meeting up at the same location to find that voltage, VB. I don't know if this confused you more or made more sense. Don't know. Okay.
So just not count the battery as like an element then? Is that?
So that would be an element. That could be an element in any of these boxes. So here, this could be a voltage source here. It would have to be 3 volts in order to make this not blow up. So to keep the rule of like, you have to keep the same voltage across every parallel branch is kind of like a law that if it doesn't, it's gonna blow up. So.
So then why wouldn't like the bottom one, why wouldn't the ground then connect back to the battery since it's technically the same wire?
Yep, all of these would be connected. So I could draw a wire here between all of these if you wanted, and just have one ground low. One.
The previous one, the pump looks just like, why is the yellow going to the ground then through the battery? Why is the 0 volt going to the negative side, not also for the?
Not through which point?
The 0 volt reference is not also purple to the negative side to the batteries. Isn't that the same node essentially?
So the node itself that's 0, so I was just drawing and highlighting the pathways there. But the node itself is going to be up to an element. So all of this is your node location. Anywhere I measure on that node is going to be 0 volts. So here would be 0 volts right here at this location. If I did here, it would be 0 volts. Here it would be 0 volts. Anywhere along there is going to be 0 volts. So what I highlighted was a pathway, not a node on this one. All right, any other questions? Yes?
So does it matter where you start to determine that voltage?
Start as far as,
Like, do you have to start at ground and then like go left or start at ground going right, or can you start at VB or a corner or?
oh, yeah, so you can start at VB, you could start at a corner. The hard thing though with the ground, like if you don't start at ground, and I usually say I like to start at ground because it can get confusing because grounds can be connected somewhere else. And so it's really easy to make an error of going through another pathway and you've actually created 2 pathways and not realized it because of that ground. So I typically recommend to start at ground, but theoretically, yes, you could start anywhere as long as it's just back to the same spot and you ignore the ground. Okay. All right, other questions? Okay, so okay, like why is that not? Okay, I'm gonna just erase some of these so it's not so messy looking. Okay, so I notice on these that Vx is on both of these, which means that it's the same value up here and up here, right? Both of those are Vx. So I could actually draw just a wire, physically connect them, just use one battery instead of 2 batteries here because they're the same voltage. So I could then take this off. And have a circuit that looks like this instead. So that is the same. All I did was connect a wire here instead and remove the second battery. So this is the same circuit. Now, if I have changed, so say our strain increases, what happens here? So say our strain increases in value from like a base value. So if it increases, then I'm probably most likely going to increase VA. So VA is going to increase. So let me use numbers here. So say our strain equals 1K, R1 equals 1K. So if this is the case, this is going to give me Vx over 2. It will be 1K over 2K. So it will give me a half. What if our strain increases to 10K? VA becomes 10K over 11K of Vx. So it is decreased, right? Or whatever, 1 over 11. Point something. What is that? Ten divided by 11. 0.9, so it's increased. So 0.9 Vx, this is 0.5 Vx. So it's increased in value. If it goes down, so say it goes to 10 ohms, then VA will be 10 over 1010 Vx, which is very small. 0.01. So it's going to make that number really small. So you can see as it changes now, it's going to either increase or decrease a voltage value. So if R3 and R2 and R3 are all fixed numbers, and I take VA minus VB, this is going to give me basically a reference voltage to compare to. So if I put VA minus, or let's put VA and I can't talk, sorry. Let's set R2 equal to R3 equal to the 1K. Then we know that VB is 0.5 of Vx. If we use this as a base, or I call it a reference value, and we take VA minus this reference value, that's going to give us just the change itself from in VA, and that would be due to the strain gauge itself. So we are going to take the difference between the two, and it will just show us the difference in change. Does that make sense? Okay. So this is another way you're going to see this drawn. This is the same circuit. In this case, these were swapped. A and B is swapped in the diagram above. So you have I can bring this down. So note that this is the same circuit. It's again just drawn. I called my VA the other side, so I'm going to just swap these here. So I called this one VA and this one VB. But those are the same circuit. guess this is R1 and this was R2. Okay, so this is actually a chip that you can get, and it's already has these resistors on there. So they'll have either 2 resistors or all 3 of them, and you can externally add in this strain gauge. So another way you can do this is to make strain gauges in all 4 of those locations. So you could have strain gauge 1, 2, 3, 4, and then they're going to be comparing against each other for every single change. So this is one that's going to get a lot more sensitivity out of it. Okay, so on this, so this is kind of like a question that could be asked. So now this Wheatstone bridge, so say we have R1 and R3 are known. So you have 2 resistors that are known. You adjust R2 until it is giving you a voltage difference of 0. You're gonna, you know that, solve for the unknown R4, which is your strain gauge. So let's put this as R4. So if you have 0, what was your VA value? So what would be your equation here for VA? V source times, I'll put your ground in there. There's your ground. So VA is going to be the measurement across which resistor? So I would do R2 over R2 plus R1. And VB is going to be V source across which one? R4 or R strain, yeah, correct. And then it's between R3 and R4. So VAB is going to be the difference between those two, VA minus VB. So V source, and then this one will be R2 over R1 plus R2, minus R4 over R3 plus R4, and that's going to equal 0. So this will remove out the V source. I can take that over to the other side of 0, and then we have R2 over R1 plus R2 is equal to R4 over R3 plus R4. And then multiplying these over to both sides. You get R3 R2 plus R4 R2 equal to R4 R1 plus R2. And then R3 R2, and bring this over R4 R2. And then combining those together and dividing them. Negative R2 plus R1 plus R2. Those cancel. And so you're just R1 division over there. I'll cross it off here. Okay, R4, R1 plus R2 minus R2. Okay, So this would be, the R4 is going to be R2 times R3 over R1. So say these are all the same. So say they're all 1K again. You've got, or did I do something wrong?
Oh, I was just gonna ask if you were able to zoom out to see the first few steps as well.
Sorry, do what?
Can you zoom out so we can see the first few steps?
Okay. I'll back up. There we go. I gotta get out of the way for a minute. Okay, so this then gives you a way of saying, like, if I know what these values are and my strain gauge changes, if I set VAB to 0, which is usually what you do, you're able to determine what that strain gauge is. And then that will help you identify which way did it deform, how much did it deform, and be able to use that information. Yes.
Why are we able to say V source is 0?
You divide, it's equal to 0, and then you divide 0 by that number.
But how do we know that V source is 0?
You don't know what V source is. It could be 10 volts, it could be 5 volts. It doesn't matter though, because you're comparing the two by subtracting them. So because you're subtracting them and they have the same source in them, it's subtracting that out. Okay, any questions about the Wheatstone? Yes.
So VAB, VA, what's VB?
VAB is, so whenever you see any variable that's a voltage and it has two subscripts, it's meaning that it's taking the difference between those 2 points. So you would take the first and subtract the second. And that means that the red probe of your multimeter is placed on the first notation A, and then your black probe is put on to B. So it's giving you a voltage difference between 2 locations. Is that more clear? Thanks for asking. Good question. All right. Any other questions about the Wheatstone bridge? I guess this would be another question before we move on. Okay, so say I put R1 and R3 to be, they're each 1K, and I measure R2 to be 4K. And I set VAB is 0 when I measure it. What will be the value of R4? 4K, right? Somebody said it. What if I change the voltage V source from 10 volts to 5 volts? It's still going to stay 4 volt or 4K, right? The voltage doesn't affect the measurement itself. So you can have any change in voltage, it's not going to affect your measurement. If I already know what that variable resistor is and the 2 on the top are the same, it will be exactly the same because your VAB is 0. So in order to get 0 here, this resistance branch and that resistance branch needs to match each other, right, because of the divider. Okay, does that make sense? Okay, so those are some other questions you may see on the homework. Okay, so the next topic is called superposition. We have lights up here. Oh, we do. Okay, I like to describe superposition. Okay, so you have the light that's illuminating from this screen that gives you a certain amount of light and illumination. If I add on another set of lights, what you actually are seeing is the combination from here and from there. And if I turn on another one, you see it from all of those sources. What we can do is, with what are called linear circuits, is we can say, let's find just the illumination from this one light, just the illumination from this one light, and just the illumination from this one, add them all together to give us the total. That's what superposition is. So we are going to actually turn off some sources and so this works if you have more than one source. So if you have just one source, this won't work. So more than one sources, you're going to zero out all the sources but one and find the result from that. And then you're going to turn off all the other sources, turn a different one on, find the result of that. Turn off all the others, turn on another different one, find the result from that, and then in the end, you're just going to sum up all of those answers to give you the total amount. So when you turn off a source, yes?
You said it was in a linear circuit?
Uh-huh.
What do you mean by that?
So you don't know yet? So assume everything you are going to work with, it will be linear. So a linear just means that when you apply a certain input, you get out an output based on more of a linear graph like this.
Okay.
So, I guess down here. So as I put in, so a resistor is a linear element. You put in 4 volts across a resistor, you get a corresponding exact amount of current. A nonlinear device actually has a curvature to it, and so it doesn't respond exactly the same for every input. So that's the difference. And we're not going to talk about that in here. That's a little bit more depth than you need. So, and there's ways to making a nonlinear device linear and then using the same techniques. So let's talk about what do we do when we have actually created a voltage source that's 0. What does that look like? A wire, correct? A current source is a new one for you. So what happens with a current source when it's 0 is it actually looks like an open, right? Because you have a dangling wire. Remember that from the video, like if it's not connected to anything, a dangling wire, no movement of those little balls that were in the tube. And so you have 0 current, that's an open circuit. So that's how you're going to model these. So if you turn off a source, if it's a voltage source, you're going to replace it with a wire. If it's a current source, you're going to actually put an open at the location of where it is. So again, once you've replaced all sources but one with the 0 wire for voltage source, open for current, you're going to then analyze the circuit to find whatever voltage or current you're trying to find in there. And then you're going to find it for the other ones off and that one turned on, so on for all of the sources, and then sum the results together to get the end. So here's an example. So in this case, can't remember what I solved it for. Let's solve for I2. Okay, so we're going to use this technique to solve for I2. I have a current source code, can I use a current source here? Or I mean a current divider here? Cannot use a current divider. So because of this source here, I don't have parallel branches of just resistors. So I can't use a current divider here. But if I remove, so let's eliminate the current source and apply the voltage first. And with replacing this, remember a current source goes to an open. So now can you find I2 easier? So go ahead and compute I2. And this battery may look a little bit funny, so I'm going to tell you that you can use plus and minus there. So the small line is what's defining where the negative is on there. So that would be plus to minus.
What's the circle here?
A current source? Yeah. So a current source sets that branch to have that amount of current that it sets. If it's 2 amps, that will set that current branch to be 2 amps.
And it doesn't change for example.
It doesn't affect the voltage. It will have a voltage response. Every element has voltage and current. Correct. Yep. Okay, correct. It is 20 milliamps. So going through here, I'm going to make sure that I label this one because it wasn't labeled. The same current's going through that resistor. So if I take my pathway around that way, it's going to be a plus, minus, minus. So plus 6, minus. And I2 is going to flow here because there's no current here. So that is also I2 there. So I2 100 minus I2 200 equals 0. So I2 is 6 divided by 300. For 20 milliamps. Okay, questions about this one? Okay, so now we're going to eliminate the voltage source. What do we do to the voltage source? Correct, it will be a wire. So we're going to remove it and put a wire in there instead. So now you could use a current divider if you want. Or you can do a summation of current and do a voltage loop around the resistances. So take a second to solve for this one. What? Sorry.
1/3 of That's why I asked for 2/3. Sometimes wait, is this jive? What? I'm not sure about the sign, but it's an equation divider. And I think about it like in terms of
So it looked like a consensus on the value, but the polarity was not in the right polarity. So if your current matched the flow here, it would actually be going into this node to match the polarity going in there. But because the wire is drawn opposite that, it's going to be a negative of the current divider. So if I used if I notice this is a current divider and I use a current divider equation, I'm going to call that I1. Then I2 would be a negative IS, which is 18 milli. And then 100 over 300, or I could say it's negative 18, 1 over 200, and then 1 over 200 plus 1 over 100. Was it 6 milli? Thank you. Like, I'm pretty sure it was 6 milliamps. Okay, if I don't see that it's a current divider, I can still solve the circuit. If I didn't see that it was a current divider, I could start, I would call this with the point I'm starting, so my reference point, or 0 volts. I would go through this, and going around in this direction, I would go through this one, and then this would be a plus to minus based on the direction of this current. So here I would say it's a minus VR1 minus I2 times R2 equals 0. And VR1, I notice, is a negative I1 times 100. So this would be, plugging that one in, it would be plus I1 100 minus I2 200 equals 0. So I have one unknown, or I mean one equation, but two unknowns. So I need another equation. The other equation I can get by a current summation in this node, or in the bottom it would be the same. Going out is I1, going out is I2, and going out is IS, so it would be I1 plus I2 plus the 18 milli equals 0. So plugging, just picking one of these, 18 milli, or minus I2. So picking I1 to solve for, because I want to solve for I2, and then I could put this one in here for 18 milli minus I2 times 100 minus 200 I2 equals 0, and solving that, I end up getting the same value, a minus 6 milliamps. All right, questions? Do you guys follow those steps? Okay, so now we have two answers for I2. We have 20 milliamp and a minus 6 milliamp. So we just sum the results. And that will be our total. So I2 total will be the 20 milli minus 6 milli for 14 milliamps. And that would be my answer for this. Okay. So a few more involved steps as far as you have to break up the circuit, but most of the time when you break up that circuit, it's going to be something simpler, either Ohm's law, you could see it's a voltage divider or current divider. Otherwise, you could do the same steps that I did here as far as taking the loop and include the voltage source and then taking the current summation. And get the same result of 14 milliamps. So with superposition, the nice thing is you have another way of solving the circuit. So this is just a technique to give you multiple ways of solving the circuit. You can do them both, and then you can check and make sure they're the same. And it's given you a way to check that your answers are correct. Yes?
When you were summing I1, I2, and 18 milliamps, like
Uh-huh.
a little bit further up, why is the 18 not negative?
I1 minus? No, it should. Thank you. That was just my error. It should be a minus. Yeah, there's some that way, and then I take it over to the other side, it should be a minus 18 milli.
Okay.
Yeah, thanks for catching that. Yes?
So do Kirchhoff's rules still apply when there's a battery and a current source?
Uh-huh. So yeah, if I had a battery in there, then here as I go around the loop, this would be a plus, that would be a minus, and again, this is still a minus. So your loop here would be plus 6, minus VR1, minus I2R2. So you would just have a little bit different equation, but it would be still valid. Okay. Okay, let's go ahead and start this one. We have a few minutes. So using superposition to solve for this one. So you have, again, two sources. And you're going to remove one. So let's just look at first eliminating the current source and solving for the IR3, the current through there. So try to find that IR3. On this one here. Another hint. So at the red wire, what is my voltage right here? 0 volts, okay. On my green wire, what is my voltage, say, right here? 12 volts, correct. And right here's 12 volts. And notice that the R1 is in parallel with the branch that has R2 and R3. Still getting blank looks.
For some reason, you were thinking this was voltage, so it's like, well, now they voltage line here. But then since you have to base it, then you can use the original resistor. Like, so can you say VS? I know.
That's the current action.
The current is the same as here. You solve for the current here.
I just got this. I got 6.5. Well, that's going to give you the current at this point here, and you have to read the right? Because they're parallel. So you take this current.
Okay.
And you,
That's good. That's what I had.
Okay. Okay, forget some people. Okay, so minus 2.4, there's one in milliamps, and there's one that's not in milliamps. So which one's the correct one? Milliamps, why?
Because they're K.
So don't forget the unit. So K means 1,000. So if you notice, you can see that that wire is green. It's 12 volts. So I know the voltage across two resistors in series. I can use a divider. So if I know, or I can do the, since I'm finding current, sorry, I know the voltage across them, and then I can just divide by the resistance. So using Ohm's law, it would be 12 divided by 2K plus 3K. So 12 divided by 5 was that 2.4? Sorry.
Yeah.
2.4. Okay, so now question is, where did the negative come from? And because the voltage is going to be in this direction, these are going to be opposites. So it would be a negative of that, a negative 2.4. Okay, so if you want to look at this as an exercise, we'll go over the rest of it next time. Remember to do your assignments, homework for tonight, and the quiz will be open for tomorrow.
I'm going to show you how to